All right, let's go over center of mass for integral calculus. So this is calculus 2 usually in most colleges and universities, and you can get there for here. It's also in the description. This is the first long form video, so I'm not used to being able to include things in the description very easily like that. Okay, so let's go through center of mass. It's for, again, integral calculus. So here's our formulas for center of mass. And all I want to do in this video is I just want to talk about where do these formulas come from. So understanding these formulas and how they are created unlocks the learning, and that allows you to level up and learn harder things. You're not going to need to remember these formulas necessarily after your exam. That's not what's important. What's important is that you took the time to figure out why they work, and that's what's going to allow you to understand harder concepts in the future. That's what you want to take. So let's go through that. That's all I really care about. That's all the fun stuff anyway, is understanding why these things work. And I never really had the time to go through them when I was in university. That's the other thing that really sucks, is in university when I was taking this for the first time, everything's moving so fast. You have so many things to remember for your exam. You know, this is one lesson. That's one day. There might be, another lesson the very next day, or maybe even another lesson the same day. So you don't really have time to memorize all the whys and where does everything come from. You just need to know, okay, this is on my exam, so I'm gonna just memorize this formula. It really sucks. It really does. That's all the fun stuff is taken out of it sometimes when you crush too many concepts in at once. Or at least maybe I wasn't smart enough to understand the concepts that quickly, but here we are. So all I want to do in this video really is talk about X bar. Where do we get X bar from? What is X bar? We'll go over what it is, and then where does this formula come from, and why does it make any sense? Okay, so what is the center of mass, first of all? So yeah, you could think of if you had a plate, if you had a big plate, an oddly shaped plate, but it has to be uniform thickness, okay? If you have that shape and you want to just balance it somewhere, like where do you put your finger for that plate to perfectly balance on your finger? That's all the center of mass is. It's what you think it is, actually. So that's what we're computing. Now, X bar is just the X coordinate of that. If you were to put that metal shape onto a grid and find the coordinate of that center of mass, it's going to have an X coordinate and a Y coordinate. So we're looking for the X coordinate when we're talking about X bar, and then Y coordinate obviously is Y bar. All right, so all this text, by the way, is friggin' awesome. I took a long time to write this with AI. It's friggin' awesome. So go through this. This is the lesson that you actually need. The textbooks I always find are a little bit hard to understand, at least for me when I was going through it the first time. So I wrote this for me, how I could fully understand the topic in plain English where possible, but I used examples. So I used this example a lot, going through every single step so that you can understand the concepts more easily. Because that's what I had to do. I had to use this picture to understand it. To be honest, I just went through it now, or like in this past week, because I realized I didn't really know where that formula came from. So I just took the time to understand it and write up this page on it. So let's go through it. So the first thing we want to talk about is leverage. I'm going to introduce just this term leverage, which we're comfortable with and we know about, to explain this concept. We're going to need it. It's not a mathematical term and you're going to forget about it after we talk about center of mass. But leverage, we understand, if you wanted to lift something heavy, if you want to lift like a heavy boulder, right? You want to stick a stick under that boulder. You want to put a little, I think it's called a fulcrum or something here, under the stick near where it goes into the ground. And then the further away it is, the more leverage you have to press down and lift that rock up, right? That's leverage. And the longer the stick is, the better, the more leverage you're going to get. And the more you press down, the more leverage you're going to get. Those are the two elements of leverage that we're going to need for this lesson. It's how far away are you pressing and how much are you pressing? That's leverage. So now let's bring it back to this picture here. Okay, so let's say that we want to compute the center of mass of this purple region. So that's between A and B, that's the function sine x plus 2. Okay. So this has a leverage. Now, how does a shape have a leverage? Now, we're going to consider that this purple area is a metal plate. And assume that metal plate, it's not falling down. So the ground isn't here. The ground is not the x-axis. The ground is actually we're looking down on this metal plate. And the ground is the xy coordinate. So we're looking down. We're in the sky. And we're looking down at the ground. And this metal shape is flat on the ground. And it's got a uniform thickness. And in this case, we can see through it to see the grid behind it. But it's our metal shape, okay? And it's falling into the ground. And we're going to assume that it's attached somehow to the y-axis. And so if it were just allowed to free fall, it would just swing around the y-axis. It's attached to that y-axis, so it would just swing around. And so that's how we're going to think about leverages in relation to the y-axis. It's going to rotate about the y-axis. Now let's go back to distance and force, because that's what we were talking about with leverage. Let's tie those things together right now. So the further this purple shape is away from the y-axis, the more leverage it's going to have. The more power it's going to have to go in and through the ground and rotate around the y-axis, if it were doing such a thing. And now what about weight? What about the force aspect of leverage? Well, that's just, in this case, we're going to consider a bigger object to have more weight. So the area is the weight of this object and going to contribute more to the leverage. So that's weight and distance. So this one has, if we move this exact shape further to the right on the x-axis, it will have more leverage. Or if we increased its area, it's going to have more leverage, more oomph into the page. All right, that's great. So that's leverage. Now, the next thing we're going to talk about is heavy dot. I'll just refresh us that we're looking for x bar right now. Right now we're just talking about x bar. Where is the x coordinate of the center of mass of this object? Now, to help us understand, an interesting way to think about this, we're going to introduce this sentence here, this one right here. Ba-boom. And you may need to read it a couple times when you're studying after this video. And I encourage you just to read it as many times as possible. If you're not getting it, usually you need to read it a couple times, take a sleep, wait a day, and your brain figures out all the pathways while you're sleeping. And then the next day, you'll be able to understand it. If I took the entire area of that region, crushed it into one single heavy dot, and wanted that dot to produce the exact same leverage about the y-axis as the full shape, exactly where on the x-axis would I have to place it? That's what we're going to talk about now. Squishing this whole purple area down. We have this whole purple area. I'll use this image above before we introduce new concepts. We're going to squish it down into one dot and find a place between A and B that we would put that dot so that it would have the exact same leverage as the original shape. All right, so now let's compute the leverage of this thing. It's like, okay, well, if we want to do that, we should probably know the leverage of the full shape. Let's compute the leverage of it. To do that, this is integral calculus, of course, right? You can bet that there's going to be an integral involved. And that comes when we compute the leverage of one slice and then we add them all up over our interval. So let's just pick a random x. Okay, here we go. We did it. Good job. Let's look at that slice and compute the leverage of that slice. Well, it has a thickness, right? This thickness here, we can just call it dx. It's just a little tiny thickness. It's got a height, which is f at x. So that means it has an area. That's f of x times dx. That's the area of our slice. It also has a distance away. By the way, remember, area of that slice is the weight. That's what we're calling weight here for our leverage, because what we're computing is the leverage of a slice. The distance away from the y-axis is just the x value. So now we have distance away from y-axis and the weight. Those are the two things we needed to compute the leverage of a thing, and in this case, of this slice. All right. And we see that right here, x, which is distance away times the area. And now we want to assemble x bar, or at least let's talk more about the single heavy dot. We want to add up the leverage from every slice. That makes sense. This is going to give us the leverage of that whole purple region. So we just integrate the leverage of one slice from A to B. That gives us the leverage of that entire purple region about the y-axis. Yes, very good. And now we're ready for single heavy dot. So let's read this together. Relate the total leverage to the heavy dot. The dot has the same total area as the whole region. Because remember, we're just imagining that we're crushing this region into one point. Okay, so our single heavy dot has the whole oomph, the whole weight of that entire purple area. If the dot, call this total area A. Okay, so that's the total weight, is capital A. If the dot sits at the horizontal coordinate x bar, that's just an x value like 3 or 4 or 3.5 or something like that, its leverage about the y-axis is weight times distance. So that's total area times distance from the y-axis. That's the same we've been talking about this whole time of what leverage is. For the dot to match the full shape, that is, for the dot to match the, let me just go here. For the dot to match the leverage of the full shape, maybe I should have added that word in there, but I said it here, it's good enough. We have this. This is the leverage of the full shape when we computed it with integrals. And then this is the same leverage of the full shape because it's the same weight at the right distance away, the appropriate distance away, x bar. And then you can see very clearly, if we were to solve for x bar, we just divide by A, we divide by the area. And we get our formula. That's the formula for x friggin' bar. Yes, friggin' did it. All right, so we're also going to talk about y-bar. Y-bar just for a second, and then we're going to go to some examples. I'm going to show you here what I built for you. So for y-bar works the exact same logic, except now we're measuring leverage about the x-axis instead of the y-axis. And then without turning this into a novel, we'll leave it there. It's the exact same thing, except you want to think about how much does each slice contribute to leverage about the x-axis. And then you add those up, you do single heavy dot, exact same thing, and then you'll get it. So now we have a bunch of examples. This is all free. It's all in the lesson. You're finding different centroids here. This is enough of a centroid between two curves. I forgot I included that. Brilliant. I mostly included that because there's an exam question that I have here on the site that does centroid between two curves. So that's why I included that here. On your exam, you're probably going to get this. So yeah, that's ultimately a reasonable exam question is going to be centroid between two curves. It's not going to be just a standard function like we did in the example. We did a very simple example to give you the concept, so now you know the concepts, but on the exam it's going to be much harder. So here's a little baby example, centroid between two curves. Make sure you do that one. There's center of mass with variable density because we did a constant density, so it's a little bit more difficult with that. Moment is what we were calling leverage, by the way. So that's what moment is, the word moment. Good examples. And then we have, at the bottom of this lesson, we have common mistakes. So this section I have this in all my lessons is the most common ways students lose marks on exams. And then we have, of course, the formulas that we used. You've seen them all there. We went over them all. So that's it. So you can use this. You don't need your textbook. If you can go through everything and understand everything that's on this lesson, then you understand center of mass better than I would say 95% of the students in your class, because what are they going to do? They're going to learn the formula. They're going to learn this formula. They're going to do a simple example with it, and that's basically where they're going to stop. So for you, you're not going to stop there. You're going to have the understanding now because you spent the 20 minutes to watch this video and think about it. And now you're going to have no problems when they give you tricky true or false questions or tricky multiple choice questions about this. All right, that's it. Go study. Good luck. I hope you found this helpful. I have no followers. I have no subscribers. So if even one person finds this helpful, that would be really awesome. That would be so cool. I hope that this helps just one person. That's all.